Yeah, thanks a lot for the invitation. So I'll be talking about my theoretical work on modeling transport in strange metals using models with spatially random interactions, and also how my results fit into the context of what is known from experiments. So the outline on the talk, I'll first talk about some constraints on strange metals from transport experiments, many of which have actually been discussed in this conference already. And then I will, with reference to LSCO in particular, where you get extended strange metal phase instead of quantum critical point, I will talk about models with spatially random magnetic interactions and how one can get phenomenology that's similar to what's seen in LSCO experiments, and not just transport, but also phenomenology related to spin fluctuations in LSCO measured by neutron scattering. And then finally, if time permits, I might talk about enhancement of strange metallicity in this 2D Yukawa SYK model, which has spatially random interactions by Mottness, or the effects of Hubbard U pushing the system close to a Mott transition. So let's get started. So strange metals are, as has already been talked about, they're the normal state that gives rise to high TC superconductivity in materials like cuprates, and they have an electrical resistance at linear in T over a wide range of temperature, and especially down to low temperatures as well, where conventional metals are supposed to be T squared at low temperatures due to Fermi liquid theory. And the traditional picture is a strange metal is driven by fluctuations at a quantum critical point, and you get some phase diagram like this. And while others have talked about how strange metal resistivity is T-linear up to very high temperatures, and it comes close to this Iofe-Regel value and things like that. What is especially interesting for me is that you get the T-linearity down to very low temperatures as well, as can be seen like in this experiment with cuprate. Of course, it requires suppressing the superconductivity using a magnetic field. And there are also other materials like heavy fermions, which are different, but they also show strange metallicity down to even lower temperature scales because the energy scales in those materials are much smaller. So this low temperature behavior of T-linear is why people, one reason why people talk about the quantum critical point scenario, because you have gapless fluctuations down to zero energy for scattering electrons. So as Peter Armitage very beautifully showed yesterday, that the transport scattering rate, the momentum relaxation rate in strange metals is much larger than the energy relaxation rate, especially in cuprates. And that means that there's the T-linear resistivity in strange metals not arising due to electron phonon, but it's electron-electron mechanism. So even though it's electron-electron mechanism, one can still ask the question, are there some emergent quantity among the electrons, some two-particle boson, which is like a phonon, like it acts as a thermal bath, and you have quasi-elastic scattering over that thermal bath at temperatures much larger than some effective Debye scale, and you still get T-linear resistivity from that. But the scattering in strange metals is not quasi-elastic, and that is quite clear from these optical conductivity measurements. And optical conductivity fits this frequency-dependent Drude formula, and the scattering rate that is extracted is a linear in energy function, so it's linear in T at low T and linear in omega at high omega, and it has a almost omega over T scaling. This shows that the scattering, since it's so strongly frequency dependent, can't be elastic. It's inelastic scattering. If you took your Debye frequency Holstein type scatterers, then in the T-linear regime, they do not give you this kind of omega dependent scattering rate. And you not only see this in transport, but you also see in the single particle version, where the single particle decay rate also behaves like this in photo emission. So So the upshot is that the electron scattering processes in strange metal are momentum relaxing, of course, because they give rise to resistivity. They are also inelastic, and they are electron-electron processes, not electron-phonon. So given these constraints, we have two possibilities. One is they could be Umklapp processes, but in a single band, clean single band system, like suppose that some people think the cuprates are clean, but if you do consider it as a clean single band system, then it's difficult to have strong enough Umklapp to get T-linear resistivity at very low temperatures, because the short wavelength fluctuations required for Umklapp are typically gapped, or they don't couple to the entire Fermi surface, and only to some hot spots or something. So you can't. It's not at all easy to get T-linear at T going to 0 from Umklapp in such a system, and I don't think there is. Yeah, it's T square, so you can't get T-linear out of it. Yeah. And I don't think there's any proper, reliable calculation that produces it either. T square, of course, you can get T square, but so the other option is you want a momentum relaxing inelastic scattering as to somehow involve disorder. Disorder is abundantly present in cuprates, especially in things like LSCO, and it's hard to ignore. But the usual textbook treatment of potential disorder is elastic scattering. Your electron comes in with some energy, hits your random potential, goes out with exactly the same energy. And that's not good. So you need something more than elastic scattering from disorder. But you can have inelastic scattering too from disorder, and that is because you have a strongly correlated system. So you're not just going to have a random potential in your effective Hamiltonian. Even the interaction terms are going to be spatially disordered. So interactions produce inelastic scattering, as is well known. And if their interactions also disordered, they also relax momentum and current. So then you get exactly the combination of factors you want. You have inelastic electron-electron momentum relaxing scattering. And this can possibly produce large temperature-dependent and energy-dependent resistivities, even at very low energies. So this disordered interaction in terms of an effective model is not an alien proposition. One could, and there are actually signatures in experiment that actually happens. You can look at like this experiment, for instance, is a mercury-based cuprate and some doping where it has charge density wave, patches of charge density wave order. And since the dopants are at some incommensurate fraction and they don't go in a regular pattern into your lattice, you have these random patches of oxygen dopants, and the charge density wave order puddles are anti-correlated with those patches of dopants. And if you think about some effective model where you have some interaction that leads to CDW formation, that effective interaction is going to be strong in some regional sample and weak in some other regional sample, and that gives you these patches of CDWs. And then you just have disorder in that effective interaction strength, and that disorder is coming eventually from the dopant-induced disorder in the system. Like taking that idea of disorder in the interactions and going into a model world to try to create models for strange metal phenomenology. Like a few years ago, we worked out what is known as this 2D Yukawa SYK model, which is a Fermi surface of electrons that is coupled to some scalar field phi that's going quantum critical. And not only do you have a random potential in the system, but you also have a randomness in the interaction, which is electron to boson interaction, the Yukawa coupling. So you have this G prime of R, which is a spatially random coupling. And then, so we've, in in these papers, you get a phase diagram where in some large N Migdal-Eliashberg treatment of this action, you get a quantum critical point as a function of the mass parameter lambda of the phi field. And around that quantum critical point, lambda c at finite temperature, you have a critical fan with T-linear resistivity, which helps, and like for lambda larger than lambda c, it crosses over to a Fermi liquid, and at lambda less than lambda c, you get some ordered phase of phi. That T-linear resistivity arises because your spatially random interaction is leading to low energy boson fluctuations, being able to scatter electrons by large angles on the Fermi surface and relax momentum, because the interaction vertex doesn't conserve momentum. And in 2 dimensions, the quantum critical theory produces this marginal Fermi liquid self-energy, which also counts momentum relaxing processes, and therefore that gives rise to a linear in energy single particle as well as transport relaxation rates. And then that translates to having a T-linear resistivity and also an omega linear optical scattering rate. And if you look at the optical scattering rate as a function of omega, you see that it does behave qualitatively the same way as what is seen in experiments. So the other features of this large N Migdal-Eliashberg 2D Yukawa-Sachdev model is that it also has a superconducting instability at low temperatures. And if you study the superconducting instability at different values of the Yukawa coupling, you can extract, for each coupling, you can extract a coefficient is the slope of the T-linear resistivity at the QCP. And you can also extract when that's above TC, and then you can also extract what TC is. And they are positively correlated roughly that the slope is proportional to TC, which is also something that has been talked about from experimental phenomenology. And furthermore, if you tune away from the quantum critical point, TC, of course, goes down, but the superfluid stiffness increases, which is also an interesting feature. So that was all in this large N language where I only solved Migdal-Eliashberg equations for the model, which is obviously fairly restricted. And if you want to get closer to reality, you don't want large N. You want to do some calculation at finite N where you have order 1 flavors of bosons and fermions per site. And to do that, I resort to numerics, in particular constructing a sign problem-free Monte Carlo model of fermions with some random Yukawa coupling to bosons on a lattice where N is finite. And since there's no sign problem, there are very nice methods that you can use to scale it to large system sizes and extract low energy results. So the model for this has an action that is has a lot of extra indices because you need to have 2 fermion flavors in a particular form of the coupling to avoid a sign problem. But basically, it does have this random Yukawa coupling again, that your fermions are coupled to some phi. Phi is now an O3 field via some spatially random G prime of R. This phi field represents some antiferromagnetic order in this model. So you also have this antiferromagnetic form phase factor, but that's not terribly important if the coupling is spatially random. So this can be simulated with QMC at fairly large system sizes going to like 40 by 40 at temperatures of 1/80 times the hopping. And we get a phase diagram, and what we find in this phase diagram is there's no quantum critical point with this strongly random interaction at finite n. But you get like this extended strange metal phase between these two values of the mass parameter, where the resistivity is approximately T-linear. And that is interesting from the point of view of LSCO, as I will show later. So how does this finite n differ from the large n solution? Is that in this finite n model, what happens to the bosonic excitations is they become extremely disordered at low energies. So your boson Green's function, the 2-point function, is off diagonal in momentum at small Matsubara frequencies. So you can see in this plot that at like larger Matsubara frequencies, you only have a peak when Q1 is Q2 or the relative Q is 0. And then especially at the 0 at Matsubara frequency, you see a lot of off-diagonal support here. And this off-diagonal in momentum space, if you then diagonalize the translationally non-invariant full boson propagator, you find that its eigenmodes in the strange metal regime are not extended plane waves, but at low energies, they become localized. So this is a localization length that is inferred from the inverse participation ratio of eigenmodes. And this is the eigenvalue E. Small eigenvalues, your modes localize, and then there's a sort of a crossover to delocalized extended superpositions of plane waves at large eigenvalues E. But what is really interesting is now even you have this strong localization of bosons, and they're really affected by the disorder. The fermion sector is very clean, relatively speaking. If you look at the occupation in real space, it's basically uniform, and the histogram shows it's very tightly around the average occupation, not much fluctuation at all. And in momentum space, you can see a clear Fermi surface in the occupation numbers, and this is in the strange metal regime. So all the strong disorder ended up in this 2-particle boson sector and not in the single particle fermion sector. And in experiments, people often say that the single particle fermion sector is clean. You see a nice Fermi surface, the mean free path is large, all that, and that's fine. I mean, even in a disordered model, you can have that happen. The disorder can end up in a different sector, and you don't see it in single particle fermion measurements. So that is a pretty remarkable thing that we get. And then, yeah, we can also compute current correlation functions and then parameterize them in terms of a Drude formula and extrapolate to 0 frequency, our data is good enough to do that at low temperatures upon disorder averaging a lot. And then you see that within this range of effective mass parameters, you get a T-linear resistivity. So this is from lambda S to lambda G. So at lambda G, you have T-linear with smaller slope, and lambda S, you get T-linear with a larger slope, and linear in between as well. And then for lambda larger than lambda G, your resistivity versus temperature, or this transport scattering rate versus temperature, starts curving upwards, becoming more Fermi liquid-like. And in this linear region, if you extrapolate to 0 temperature, the residual resistivity is very small. And that is not surprising, because your fermion sector is actually quite clean. So you don't expect there to be a large residual resistivity. The disorder is producing a T-linear resistivity. It's not producing much of a residual resistivity because disorder in the interactions. And over here in the T-linear regime, resistivity, the scattering rate is also Planckian. So like a lambda s, you get like 0.4 kBt over h bar. So it's a order 1 number times kBt over h bar. And as I said, the residual resistivity ratio between the highest and temperature and the extrapolated residual resistivity is very large or pretty large. So, and so the other thing is, like it still has disorder, right? I mean, you have disorder in this Yukawa coupling, which is the variance of that random Yukawa coupling is G prime square. So you might want to ask, like, how sensitive is the slope of T-linear resistivity to this variance in G prime square, or to the magnitude of G prime square? And what we find is, of course, you change G prime square, right? You end up with the same phase diagram again, and you can again identify this strange metal window and these points lambda s and lambda g. And then if you go and sit at that same point in the phase diagram for different couplings, you find that your resistivity is basically the same. It doesn't, the transport scattering rate is the same slope of linear in T. And so you can like parameterize in terms of this shifted effective mass parameter normalized by your coupling strength. And then your resistivity becomes a universal function of that. So at low energies, this thing is flowing towards some universal state where it doesn't matter how large the interaction disorder was in the UV. Of course, the temperature, the energy window of universality will still be sensitive to G prime square, but as long as you are within that window, your physics is not sensitive to it. And that's a very nice feature in terms of what's seen in experiments where you have several different cuprates. They are prepared with different chemistries and different processes, and they presumably have different amounts of interaction disorder in the UV. And yet they all seem to have pretty much the same transport scattering rate in the strange metal phase. And they get alpha around 1, whereas I got 1 out of 0.4, but that's just features of my model. Probably can be changed in other models. This is really a non-perturbative phenomenon. If you did a Migdal-Eliashberg calculation, you will not get this feature. You will get your slope being proportional to G prime square. So it's quite interesting, and I don't analytically understand how exactly it arises at the moment, but I'm trying to work on something. And then, of course, this extended strange metal phase that shows up in the model is also reminiscent of the behavior of LSCO on this famous result from Nigel Hussey's group, where you get what is affectionately called a foot, because this plot looks like a foot. But between the ankle and the toes, you get an extended regime of T-linear resistivity where your temperature exponent is 1. And this is again a low temperature feature. Right? This is a feature of some low temperature effective theory that's describing the system. Once you go out to higher temperatures here, you start losing that. So all the nice universal physics again happening here. Of course, here you have something different, but I won't get into that. So there's So the other thing before is that I showed you what happens to the resistance here and here, but what happens if you reduce lambda even further? And if you reduce lambda further, you have these phi bosons. They form glassy antiferromagnetic order. So that's quite easy to see in Monte Carlo because your simulation starts to struggle. You get long autocorrelation times, and instead you plotted your observables versus the Monte Carlo time, you start seeing slow dynamics. And autocorrelation time also blows up as you reduce lambda less than lambda s. And then you can also look at things like the susceptibility and extrapolate it to long times. And then that becomes get an excess susceptibility that's extensive in beta, which is a sign that it's, again, the long imaginary time dynamics are frozen. So you get this frozen in time bosonic or antiferromagnetic state, but it's still short range ordered in space. The correlation lengths in space are still ordered only a couple lattice spacing or something. So that is a telltale sign of glassy order. And I mean, these ideas have been thrown around earlier in like what was called a cluster glass phase by Vladimir Dobrosavljevic in an old paper, but there was not like a full control calculation there. And this glassy order is also observed in LSCO within the pseudo-gap phase, as described in this paper. And this was what the phase diagram is. And they say they have antiferromagnetic glass at deeper within the pseudo-gap phase. So it does occur at somewhere in the phase diagram, at least. And there's a more recent paper by Cyril Proust's group in which they take LSCO and they apply a fairly large magnetic field. And then as you tune by field, you get a extended strange metal regime where your spins are fluctuating. And at higher fields, the spins freeze and form an antiferromagnetic glass. And then you get this. So they again do this kind of color plot where the resistivity temperature exponent is plotted as a function of field. And in the strange metal regime, it's close to 1. And then when it becomes a glass, the n becomes less than 1. So it becomes sublinear in T scaling. And if we look at the model, when you go into the glassy phase for lambda less than lambda s, there are two things that happen to your transport scattering rate. One is that the residual transport scattering rate now starts increasing rapidly. And that is not surprising, because if your bosons freeze, now you have a spatially random coupling to frozen bosons, which is not dynamical. So it becomes exactly like a random impurity potential, and that we all well know gives a residual resistivity. And the other thing is the temperature dependence becomes sublinear in T, which is also nice. I mean, that's also what happens here in the glassy phase. And now going back to the strange metal phase with this linear in T and like 0.4 kBt over h bar maximum scattering rate. This also is reminiscent of this stability bound logic for Planckian scattering, which was proposed in this paper. And that this paper argues that if you have a T-linear metal, then and you crank up the coupling, crank up some effective coupling in the system, it's eventually going to have a phase transition into something else. And that the existence of that phase transition puts an upper bound on the T-linear scattering rate that you can get. And that upper bound is order kBt over h bar. And this paper demonstrated it for like this bipolar on transition in Holstein models. Here in this work, we find it happening due to this transition into a glassy phase. And in both cases, it's a non-perturbative phenomenon. This is not something you can capture with Migdal-Eliashberg theory. You have to do numerics. So that's that. Okay, so this is all the transport stuff. I also have some results regarding spin fluctuations experimentally observed in LSCO and calculated using these models. And that is in this paper. And so this paper is mainly an experimental paper. by Stephen Hayden's group. And they did neutron scattering and extract the spin susceptibility and the imaginary part chi double prime q of omega, which is related to the structure factor like this. And there's a phase diagram where they find this extended region of critical chi double primes, where it has omega over t scaling. And so this is what some of the results look like. So the STW occurs at some wave vector, and then the chi double prime has omega over t scaling at that wave vector and some overall power of temperature weight. And that power exponent alpha is not the Hertz-Millis exponent, it's smaller. The Hertz-Millis exponent is 1, and you get 0.32 in the experiments. And furthermore, they can also look at wave vectors close to but away from the STW wave vector Q delta, and then parameterize it in terms of like the squared Lorentzian function. And there's this width of the peak in Q as a function of omega, which is kappa. And this kappa scales as t to the 1 over z, which is some dynamical critical exponent z, and that's what you would expect. And it has omega over t scaling as well as some value of z that they can extract in the experiment to be about this much. So we did some calculations where we tried to construct a more effective model which has these features of dirty bosons. You get all these localized boson modes over an extended phase and stuff, but which can also be solved easily on the real frequency axis. And that was done by, if you integrate out the fermions in the model I showed earlier, at finite n, you will get a random mass term for the boson. So that is and you'll also get a Landau damping term. So we take a boson theory and add those two terms to it, and then also add a self-interaction. And then you just compute using self-consistent Hartree in this fully disordered action, in not doing any disorder averaging, you're doing non-translation invariant calculation. And then you can solve for real frequency boson propagator numerically. And so you get this phase diagram, which is a bit different from the QMC, is that you actually do find a critical point. You don't get this glassy order. And you have some onset of T-linear resistivity again, which extends over some extended phase, and beyond for large mass on the other side, you get a positive power of T, like a Fermi liquid, but you still get this extended strange metal regime over here. And in that extended strange metal regime, you can take your boson propagator, which is called chi, and then you compute chi double prime. And it has this, again, at the critical point, it has this nice omega over t scaling, gets some alpha, which is less than 1, doesn't match the experimental value, but it's still smaller than the Hertz-Millis prediction. And then, away from the critical point, but still in the extended phase, the omega over t scaling is not that good. And you get some other value of alpha, but at low frequencies, you still have omega over t scaling. And then this width the momentum width as a function of frequency also has omega over t scaling, and you can extract some values of z, which turn out to be somewhat larger than 2. And like a mean field estimate of the resistivity coupling to these random fluctuations does show linear in temperature behavior at low temperatures. And you can also look at the local susceptibility, which integrates over momentum, and that has omega over t scaling over the entire extended strange metal phase. You can also do something with the QMC data, where you can look at, you don't have real frequencies, but you can look at imaginary axis, omega over t scaling. And if you go at exactly at the end of the strange metal phase, just before a transition into the glassy phase, then it does have imaginary axis, omega over t scaling, and the exponent alpha there is much smaller. It's about 0.2, so that's closer to the experimental value. And finally, this is the last part of my talk. I have to do something with strange metals near Mott transitions, which are now seen in these newer experiments on TMDs. Have a Fermi liquid on one side as a function of filling, and then you have becomes a Mott insulator. And in between, you have T-linear resistivity down to low temperatures. So we did some calculations where we take these mean field 2D Yukawa SYK models and include a Hubbard U using DMFT. So this is not a 2D calculation in the same way the QMC was. This is like a 2D embedded in infinite dimensions because DMFT, and each side couples with this spatially random coupling in the spin channel to this 2D bosonic Bhatt, on-site Hubbard U. And there again, if you tune it to the critical point, and you see that you get this T-linear scattering rate, which in the DMFT approximation is the same for both transport and single particle. And the T-linear scattering rate is enhanced by turning on a Hubbard U. So this is a function of gamma as a function of T as a function of some mass tuning parameter. So this is away from the critical point, and then as it goes from green to purple, it reaches a critical point and becomes linear in T. And then if you do that for different values of the repulsion U, you find that this T-linear slope increases as a function of U. And eventually, of course, you make U too big, you get a Mott transition, it becomes an insulator. So again, this maximum T-linear slope that you get is bounded by this Mott transition. And the maximum value that you can get is around 2 kBT over H bar, which is also like getting a Planckian bound on it, again, through the same stability bound logic. So that is the end of my talk. So in conclusion, these two-dimensional Yukawa SYK models with spatially random interactions can do a lot of interesting things, both in large N and finite N calculations. Finite N calculations, especially, you get this extended strange metal phase, which is reminiscent of what you see in LSCO. And it has Planckian scattering rates that are independent of the strength of randomness in electron interactions. The boson fluctuations in this phase also show omega over t scaling. And once you get to the strongly coupled end of the phase as a function of a tuning parameter, the fluctuations free then from glassy antiferromagnetic order, which is also a feature seen in some experiments. And so that's what I said. And finally, like Hubbard U Coulomb repulsions can actually increase the randomness of electron interaction in the spin channel associated strange metallism. And that's the end. I conclude.
So thank you. Yeah, it's a really beautiful, self-consistent story. It seems to me one important thing to do now is to start to try to understand microscopics. I mean, do you have any idea if cuprates have the right kind of disorder and enough of it to give these effects?
Yeah, so that's an excellent question. That's something that I'm trying to do now by starting to talk to first principle modelers. to see if like this, you do some non-translationally invariant first principles calculations where you take into account explicit randomness in the dopant arrangements, and then try to calculate what is like the effective Hubbard U in the copper oxygen planes as a function of position, and see how much disorder you can get. And then
rates have a lot of different, there's a lot of universality in the phenomena, but certainly different disorder landscapes.
Right. And then one can feed that quantitative estimate, how much is that disorder as a fraction of the bare coupling, and feed that number into one of these simulations and see what happens as you go to low energies. Is it enough? But the thing about disorder being of different strengths and different cuprates is something I touched on over here, that it doesn't really matter at very low energies for these models. The UV disorder can be of different strengths, but you still get the same IR physics.
Another maybe quick question. You talked about spin boson, spin fluctuations, but I would guess that these are not quite so well described, right? And they should also be seen in dielectric measurements through like basically electric dipole. Is it really going to be just spin fluctuations? I mean, is that what we're thinking about?
So I don't think that the models in the strange metallicity in these models is reliant on the fluctuations being in the spin channel. You could replace them with bosons in some other channel and it should still probably work. I mean,
it wouldn't even just work, but just be expected because local symmetries are so low.
Yeah, it's probably there, and but the thing is that these theories, these models don't really care what the boson is, so that's a good thing.
Yeah, so thank you. See, from the experimental perspective, if you see the strange metal behavior is quite universal in the sense you see it in heavy fermion systems, you see in iron-based superconductor, you also see in organic superconductors. So, because there is clear universality from the experimental perspective, so can one think of this model applicable to all these strange metal classes, or how do we argue that randomness is universal in all those systems, or we should just say that this model is only applicable to cuprates and the universality, experimental universality is...
Right, so the heavy fermions, I would say they're a bit different. They're two-band systems, and so I was focusing on single-band systems with this model. With heavy fermions, there are other things that could also happen, and I would not say that this model is like the model for heavy fermion systems. But there are universal features within this model itself. One is it doesn't really care about the type of boson. Right? So it doesn't necessarily have to be spin fluctuations. It could be a nematic fluctuation or something else, which could happen in a different material from just the cuprates. And the other thing is that you get this Planckian physics in low energies, irrespective of what the UV disorder strength was. So it's definitely applicable to, I would think, to systems with different amounts of disorder. But not all I would say like single band.
One last comment. So there is a work in 2021 by Shankar Das Sharma and Tarafdar Sarkar. So they found one counterexample to Planckian bound actually. The Planckian bound is something which has been seen to be violated in the overdoped electron-doped systems. So
violated with a T-square resistivity, in fact.
No, the T linear resistivity. The Planckian bound has been seen to be violated.
Yeah, I mean, even with a T-square, they even had T-square resistivities going over the Ferregal value or something. But I don't know if there's a T linear that violates the Planckian bound. I've not seen that data. If you can send it to me, that would be very interesting to see.
Oh. Thank you very much for your very nice talk. So I have just a comment and question. The comment is, the data I was showing in the previous talk on the electron dope sides is consistent with this scattering rate varying by an order of magnitude.
Yeah.
So I don't think
across the Fermi surface. Right?
Yeah. So I maybe in the Lagros paper that you quoted, maybe at those values that they they were looking at is approaching the Planckian, but actually across that, let's say the strange metal regime in the electron doped side, the strength of that scattering rate is varying.
Yeah.
Now, it may be that it's somehow fixed at the Planckian scale on the whole doped side. I mean, that's kind of
But also
with our thinking, but not. I don't think it's true on the electron doped side.
it also does vary in the model. So you're right. I mean, yeah. So as you go from lambda G to lambda S, the slope goes up. So at lambda S, it was 0.4 kVd/h.
I see. So when you're saying Planckian, you're referring to the maximum
yes
slope.
Yeah.
Okay.
So
A lot of people think when it's T linear, it's always at the Planckian scale, but I don't think that's the case.
no.
Okay.
The maximum is Planckian.
Yeah.
The maximum is Planckian because of the stability bound. That's if you try to go more than that, you have a phase transition.
Okay, thank you, that's clear. And the question was, you had a correlation between the slope, I think, of the resistivity and TC, and I was wondering how you obtained that.
That was done using this, using a large N mean field calculation, where you only look at Migdal-Eliashberg Feynman diagrams.
Okay.
And in that, what was done is that you tune to the QCP at different values of the coupling strength. And each value of the coupling strength has a different A and a different TC, and you just plot them against each other.
But you're saying that the superfluid stiffness increases while TC decreases away from that point.
From
in
the
the
QCP,
suprates, the superfluid density decreases as you move away, and TC decreases. So it goes in the opposite sense.
the TC goes down as you go away from
Yeah.
the QCP,
You said
but
the superfluid stiffness increases.
it also increases, yes.
Thank you for a beautiful talk. My question is methods to quantify the amount of interaction disorder. Supposing I can tune a strange metal back into a Fermi liquid,
Yeah.
then presumably the fluctuation, the scattering off the fluctuations that you have that play an essential part in your theory will also produce elastic components to the scattering,
Yeah.
which will then come into the residual resistivity. So can I not use that if I can push one of these systems into a Fermi liquid regime to quantify the amount of disorder?
And that's, and in this model, we only found that this coupling, this random coupling and this fluctuating bosons, they produce elastic scattering only when the bosons freeze and lose their dynamics, because then this phi just becomes a number, and then you're just coupling to some random potential.
Surely that's just in perturbation theory. If I have an exchange of one boson,
Yeah.
that self-energy will have randomness in it, which will create elastic scattering. It breaks translational invariance. It'll cause a residual resistivity on its own, right?
Not always. It doesn't for us.
Why?
Because the boson's dynamical. It only when the boson freezes out in that glassy region, that's when it does cause elastic scattering.
No. It will produce second-order perturbation theory changes to the energy, even when it's dynamical.
Maybe we don't really see a large elastic scatter, large residual rate. Right? So those effects are weak if they exist.
Thank you. That's exactly why I asked if we could push it into a Fermi liquid.
That's
Do you have a back of the envelope equation to explain that smallness? It would be very useful. I think.
do second order perturbation theory with the.
Yeah, just to quantify the amount of disorder.
If you do second order perturbation theory with a random coupling to a gapped boson, which will give you a Fermi liquid, you will just get a T square. I don't think you
So
see
you also get a random change in the energy of the particle at different locations.
Yeah, that probably requires higher order calculations, which you can't do on back of envelope. Yeah. But I mean, these effects are small, so I'm finding numerically.
Well, since I have the mic close by, I'll ask. The resistance, are you getting it out of the Monte Carlo using the beta over 2 method? Or how are you getting the resistivity?
So what we do is, you can compute this quantity at, what was it? And we parameterize this as some Drude weight, which we calculate exactly for the non-interacting system over and then we have this function gamma of omega n over nt, and it's an increasing function of both t and omega n, and we only have it down to 2 pi t, where we just extrapolate this function to omega n equals 0. And of course, if we did this on the real axis, then this would be, this is your frequency dependent Drude formula. So yeah, so that's what we do. We don't do the beta over 2 method, but it seems to work well.
I'm just asking, if you now look in superconductivity using the similar model, so will there be some universal feature also in superconductivity?
You mean in the in the non-mean field calculation? In the large n type calculation, I just showed the results, right?
But did you show the superconducting channels there? I see only
in the large n calculation, we have done that. Right? And in the like the non-large n calculation, where you have explicit disorder and stuff, we are working on something right now.
Let's thank Aavishkar for a very interesting talk.